Because gas particles are so different in the way they interact with one another, samples of gases are very different in the way that we look at the amount and movement of the particles. When we are trying to define gases based upon their macroscopic properties, or the things that we can measure and observe, we would think about the quantity of particles, either in moles, or it could be in particles, molecules, or atoms, the temperature of it, which we'll see is related to the speed of the particles, the volume of the gas, which is defined by the container that it's in, and the pressure of the gas. And pressure is a measure of the collisions of those gas particles, or the force from the collisions on the area. So those four quantities are kind of paired up with one another in a lot of different gas laws that explore the relationships between them. The first is often called Boyle's law, P over PV times PV, P1 V1 equals P2 V2. The second would be Charles' law, V over T is V over T. Gay-Lussac's law, P over T is P over T. And then Avogadro's law, that the volume is proportional to the number of particles. We can represent and think about these in terms of equations. We can represent them as graphs, and we'll look at graphs. Or we could think about what those relationships mean. How changing the space changes the pressure. How heating it up changes the size or the pressure. Why a different number of particles would occupy a different amount of space. All of these are put together, summarized, or able to be solved by using one equation that applies all of these variables. It's the ideal gas law, PV equals nRT. We are given that equation on the equation sheet. We are familiar with it, and we will continue to use it. R is the only of variables from up here that is not given. That's because R is a constant. It's what makes these things equal instead of just proportional. R is based upon what pressure unit you are using. We're probably most familiar with atmospheres as our pressure unit, although the AP exam does give us the value if we are using torr as our pressure unit, and also gives us 8.314. It writes it as joules per mole Kelvin, but a joule is also defined as a liter kilopascal. So if you have kilopascals and liters, you can use the 8.314. But that equation can be used to solve for any of these relationships. There's always going to be something, either one or two things that are held constant. So by solving for an unknown or solving for the things that we know, we can use this equation in place of any of those, or we can choose the correct equation for the correct relationship. An important thing to note is that these equations are not given. So do not rely on those if that's the only way you know how to solve something, without specifically memorizing which are direct and which are inverse relationships. So this is useful for all of these. It also is useful for gas stoichiometry if we're not at STP. If we were, we would likely use the 22.4 liters for every mole at 0 Celsius in 1 atmosphere. And that's good for our relationship from one thing to another. We can also think about or rearrange this equation into a different form that we are not given, which is that the molar mass is equal to the density times R times T over P. So in this one, it's sometimes remembering or think of this as the molar mass kitty. So the molar mass kitty puts dirt, DRT, on its P. We know that cats, when they go in the litter box, they cover that up. This is super helpful in multiple choice, making shortcuts between molar mass to density or density to molar mass, or understanding those relationships. All this is doing is basically substituting in grams and thinking about the relationship in grams and moles. But it's the same equation using new variables in new ways. So it's important that we practice this enough that it becomes really easy, both multiple choice, but more importantly, free response points as well.